I want to go through some of this stuff from chapter 18. A lot of this is kind of picture driven. So we talked about oxidation, we talked about reduction, but some of the things that we're going to see are based on these pictures of galvanic and electrolytic. So a galvanic cell, you're just going to think of as the battery is the chemistry. And then, I don't know if that shows up on your screen at all. So there'll be electrochemistry in terms of making a battery, and then there's the chemistry in terms of driving a reaction with electricity. And so that's the difference that we really kind of want to be careful about. So we'll have electrolysis later, which when you see lysis, you think of breaking apart. And so it'll be breaking apart things with electricity. So when we're looking at these pictures, I've got pictures here of our salt bridge and a porous disc, but we've got two electrodes and they're connected through some kind of wire. And usually a better picture would be something like this, where we have an anode and a cathode. And you're going to think of your anions and cations, all right? And so anode is like a negative electrode, all right? But an anode is where the oxidation takes place. So anode is oxidation. You can also think of this is your negative side, all right? And on your battery, and it's electrons come from this anode, all right? So oxidation is losing electrons. This is where those electrons are going to be coming from, and they're going to flow through the wire towards the cathode, which is, when you think of that, you see a positive electrode. All right, so cathode. Then when we look through these, we're also going to be talking about load. And so a load is something that's using the electricity. Typically, in the galvanic cells, that load will be whether it's as simple as a light bulb, or usually we'll be looking at a voltmeter, just something that's going to, I could show you one, but I think it's out in my shop. But it's, in fact, I've got a picture here. So it's just something here that's going to be able to show us the difference in these voltage, and kind of, you can think of volt as kind of the pressure of the electrons. And so here I've got a positive voltmeter, positive voltage, and that's kind of our key to this, is if it's positive, then it's spontaneous. And everything's going to kind of be driven around doing this idea of having that being positive. Now, the electrodes themselves are always these pieces of metal, which they don't necessarily have to be involved in the reaction itself. And so we can either have, the reactions typically take place either at the interface between the solid and the liquid, or all in the aqueous phase. And so you'll have to look at what's involved. If one of them is a solid, we can use it as the electrode. But if they're all liquids, then we'll use usually something like platinum just to conduct electricity. that's not going to be involved in the reaction. And so when we get to doing some of these, sometimes you'll see them use, for instance, a spoon or something, an ornament, some piece of metal that's part of the reaction. And so we can just use that as the electrode itself. So if you get confused on those pictures, just kind of keep in mind that that's where the reaction takes place there. Another thing I want to talk about then is, let me find one, is these kind of equations that we see here. So these half reactions, when we see them in a big list, we'll see them again in just a minute. Matter of fact, I pull up a whole big table of them, and we'll give you these whole lists of these half reactions. So it's a little bit intimidating at first. These are sort of like what we were doing with our reactions for the heat of formation, but these are the standard reduction potentials. So they're always written as reductions where we're gaining electrons. And so if we're going to be doing two half reactions off of these lists, we're going to have to flip one of these. And that's always kind of the hard part, is to decide what part gets flipped, what part doesn't. So here they've given me they've given me tin and copper, and they gave me two reactions, and they want to know, hey, which side's going to be the anode and which side's going to be the cathode. And so that means one of these reactions will have to be flipped. You can't have them both losing electrons. One of them's going to lose electrons. And so whichever one is the less positive, is a good way of thinking about it, is what gets flipped. All right, so the less positive, whichever one's negative or whichever one's smaller if they're positive. So here I've got my energy of my reduction potential of negative 0.14 versus 0.34. So the negative 0.14 is what's going to be flipped. So if I flip that whole reaction, this energy, I'm going to throw this one out. So if I flip this whole reaction, so when I take my SN, that's a +2 electrons, goes to SN, and it told me E0 equals negative 0.14 volts. It's supposed to be an equal arrow. All right, so when I flip this, then I'll have my SN goes to 10 plus 2 electrons. And when I do this, I'm going to change the sign here, 0.14 volts. But let's say I needed to multiply this. When we did heat, whatever math I did to my reaction, I would have to do to my heat. That is not true for these reductions. And so even though I flip it, so if I flip it, we change the sign of our E0 is a good way to think about it. But if I multiply it by a constant, for instance, if I do this reaction again, in other words, we multiply it by an integer, this E0 is unchanged. And that's a key difference from when we would do reactions with heat. So if I came through and multiplied each of these by 2, and I had 2 of these, and now I have 4 electrons, it's like doing that reaction twice, I'd get twice the heat. But here I will get the same amount of reduction potential, so the same voltage. We'll see later that this does actually affect the current, and it affects the amount of electricity that can flow, but it doesn't actually really affect the voltage. All right, and so the only way to really change the voltage is by picking which reaction you're going to do. And so that's why when you start buying fancier and fancier batteries, you'll see that they're made of different materials. So you've got your lithium ions and your lithium, and then and so as you buy these different batteries, they tend to all be pretty much the same voltage. And so when you get to charging them, you'll notice that you can charge so many different types of batteries with pretty much the same charger because the voltages on that charger don't change, and most of our batteries are made out of the same basic cathodes. All right, so for instance, in this example they gave us, let me get us back to that view. So they said, hey, which one is going to take place? And they want to know, hey, which one happens at each electrode? So I want to know if the 10, so I had to flip it. So that SN went to SN plus 2 and 2 electrons. Since I had to flip that, that's my oxidation. And you can see we lost electrons here. So we losing electrons. Oxidation is our anode. If you get oxidation, it's your anode. So the 10 will happen at my, the 10, and it's actually the plus 2 happens at the electron. So let's see. If I'm looking through these, the SN plus 2 will be at my anode, and the copper will be at my cathode. All right, so the other kind of issue that we run into these, we won't really deal with these, decide which one's the best. So when we get these half reactions, usually we don't give you a whole big long list like this, but even if we did, so you pick the ones that you're going to deal with, and we choose which one we flip, and we said it's going to be based off of whichever one is the smallest positive flips. And what you're trying to do is get the overall, when you add up the total voltage, that needs to be positive for it to be spontaneous.